Welcome to the 8th and final week of computational algebraic topology. Our goal this week is to study a branch of applied topology called discrete Morse theory, which is a framework to reduce large chain complexes to tiny ones while preserving homology groups. And what's really nice about it is that it's extremely flexible. I mean, we've seen tons of different homology and cohomologies. We've seen persistent homology, sheaf cohomology, and this works for all of them. Of course, it's only interesting if we can do this efficiently. So our algorithm for reducing a large chain complex to a tiny one should be more efficient than just computing the homology directly using the linear algebra methods. So that is the case. So this is why it's important to think about and work on this topic. So before we get started with anything heavy, here's just a bit of notation that's going to make life easy. So note, K is going to be a simplicial complex, which remains fixed throughout this lecture. And we're going to write the following new bit of notation, sigma less than with a bar tau. And this is going to mean precisely that sigma is a face of tau in K, and that the difference in dimensions is exactly 1. So dimension of tau is a dimension of sigma plus 1. And this is going to make life easy for various reasons, just because I want to sort of single out these codimension 1 face relations more than any of the others. So this is going to be convenient. Okay, here is a definition that gets us started, the first step towards our goal. Oops. So here's the first step. A partial matching on K is a collection. I'll write it this way, so big sigma and then some indices for its contents. So of simplex pairs in K satisfying the following condition. So one condition has already been written down. I'm not trying to sneak it under your nose or whatever. That condition is that these pairs have to differ. I mean, they have to be, sigma has to be a face of tau for every pair in here and of codimension 1. So these two conditions have to be satisfied for every pair. So that's sort of implicit now in our notation. But the slightly more serious condition is if one of these pairs appears in sigma, then none of its constituent simplices, so neither sigma nor tau, can appear in any other pair of sigma. So this is something you have to sort of think about maybe if you haven't seen the definition before. What I want to point out, if you want a sort of more hands-on perspective for what's going on, it's the following. This is completely equivalent. So let me write equivalent to the following structure. A pair S sigma, so think of this as containing all the sigmas, and T sigma, this is the one that's going to contain the taus, of subsets, and I want to emphasize not necessarily subcomplexes, of K, along with a bijection, which I'll call mu from S to T, I mean, it's a bijection, so it doesn't quite matter, does it? But anyhow, so this is a one-to-one and onto mapping between the simplices in sigma, simplices in tau, and I want to say that these things are disjoint. So how do we write that? Disjoint subsets. So no simplex in S sigma should be a simplex in T sigma. Okay. So there's a bijection satisfying sigma is less than a codimension one face of really mu of sigma for all sigma in the source. So these are completely equivalent ways. I mean, all we have done is partition a simplicial complex into three pieces, two of which are bijective, and each pair of simplices in the bijection is related by a codimension one face relation. The things that don't get touched by sigma are called critical. So the simplices in, let's give them a name, let's say C for critical, K minus the pairs, sigma union T sigma, are called sigma critical. And somehow these will be the most important ones. We spent all our time talking about the pairing, but it's the unpaired simplices that are going to play the sort of crucial role here. Okay, before we go on with the consequences of this definition or any other related matters, I think we should see an example. So here is a simplicial complex that I might draw 4 or 5 times, just because this is, I think, the minimum size you need to illustrate all the things that should happen. So 2, 3, 4, and 5. Thank you for your patience. So here are examples of acyclic, just partial matchings. And what I'd like to do is show you how to draw these. So you can draw sigma on K, the geometric realization of K, as arrows from sigma to tau for every pair sigma tau in the matching. So here are some examples. You can take this in the first of the 5 pictures. You can take this vertex, match it with that edge. So this vertex is a sigma. The edge is its corresponding tau. And similarly, you could do that here, and maybe this edge would match with the 2 simplex, and this is perfectly good. Here's another example that's a perfectly good partial matching. Here's a third one, which is not so good. This one contains these 2 arrows, and maybe this one. And the reason this is no good is because at that sigma, there are 2 paired taus, right? There are 2 edges that show up there, and that's basically not allowed by our condition that mu has to be bijection. Similarly, you could have paired this 2 simplex with these 2 edges, and that would not be allowed because mu inverse fails to be injective. That tau has 2 sigmas affiliated with it. And here's one that's not allowed for an even stupider reason, which is that we're pairing things that are that vertex and the 2 simplex, which are more than 1 codimension apart. So to summarize, this one's okay, this one's okay, and these 3 are failing our criteria. So these were 2 examples and 3 non-examples of acyclic, of just partial matchings. And on this side of the gray line, everything's okay. On that side of the gray line, everything's terrible. Okay, we're not interested in all the partial matchings. We're only interested in a very special subset. And I keep saying acyclic, so you know that that's the one we like. So let's define that. Here is the definition. So 3 parts to it, I think. So a sigma path is a sequence of cells, or simplices rather. Let's write them as sigma 1 less than tau 1 bigger than sigma 2 less than tau 2, and this keeps going finitely many times. So this has to be a distinct sequence. Sigma m, let's say there's m pairs in the sequence, so that all the sigma I tau i's are in the matching. Which is to say that this pair is in sigma, that pair is in sigma, and that last mth pair is in sigma, which forces the tau 1 sigma 2, for example, they cannot be paired by our requirement that mu is a bijection. So that's a path. And what we want to do, for reasons that will become clear towards the end of this lecture, maybe not immediately, is ban certain types of paths. So we can illustrate this already with the examples at hand. So here's a path in the first example. So here's a sigma, that's this vertex. You go up to its tau, that's the edge. So we've done this pair. So you've gone up a dimension. And now you want to drop a dimension. You cannot go back to sigma because of the distinctness. So you go ahead to the second vertex over here. And now there's a tau available because this vertex is also paired, and you go. And now when you reach this vertex, you stop. There's nowhere else. There's no arrow for you to climb up. That's the end of the road for you. On the other hand, if you tried the same game on the second picture, you could go right, you could come down, you could go left, you could go up, and you're back where you started. And you could keep doing that. And that's sort of a recurrent path. So for that reason, it's called a cycle. So let's say this was rho, and we call rho a cycle if it has length greater than 1, and the first simplex is a face of the last one. If it has length 1, then it's not really a cycle, is it? Because of it's just back and forth. But this, for higher length, you actually create a non-trivial cycle. And if it's not a cycle, that's the case we like, gradient otherwise. And these are the types of sigma paths that we are going to like. These are the only kind we want to keep around. So we call sigma, this partial matching, acyclic, which is what I keep saying, even though I hadn't defined it yet. Now I have. If all of its paths are gradient. And now if we go to our examples, which are still at the top of the screen, you're going to see that the first one is acyclic. And the second one, this is where I showed you the cycle, is not acyclic. So that's the only kind we want to keep around. So let me tell you why that's the only kind, and so you get a sense for why this structure of an acyclic partial matching is relevant for computing homology very, very fast. So here are the assumptions of the big theorem that I'm going to try and prove over the next few lectures, not this one. Let sigma be an acyclic partial matching on the simplicial complex K. That's it. That's the only assumption. And here's the output. Then there exists a chain complex and I'm going to write it as C sigma K. So there's a 0th term, and then there's the first term, and then this keeps going, satisfying 3 properties. And they're all amazing properties. So let's think about what they are. Here's the first one. CK, so the kth chain group in this special chain complex, is the direct sum over, let's say, the critical simplices. These are the ones that were not paired by the matching sigma of the correct dimension. And that many copies of the ground field F. So what this means is, whereas the usual simplicial chain complex would take the direct sum over all possible simplices that were in K of dimension, of the appropriate dimension, here we're only building vector spaces corresponding to the critical simplices, which are going to be much, much smaller. Here is the second property. The boundary maps that go from the kth chain group of this tiny complex to the k minus first one are built from, and making this precise is going to take the next couple of lectures, are built from the sigma paths. So to know what the boundary is, you have to know the structure of the sigma paths, those arrows that we were chasing down in the pictures a little bit earlier. And of course, none of this would be useful without property C, which is the homology groups of this special chain complex, C sigma, are isomorphic to those of the simplicial complex K. So if you take a second and think about what that means, we have the original way we had of computing homology would build these large chain complexes. That zero chain group would be, the dimension of that group would be, as many vertices as you had, as many edges as you had, and so on all the way up. Now there's a way to quickly pair up simplices, and when they pair up, they disappear from contention. You no longer have to worry about them. You only worry about the simplices that you weren't able to pair up, and those form the chain groups, which means that this reduced matrix, the dimensions of it are going to be much, much smaller than they would have been in the ordinary simplicial chain complex. And miraculously, even though this chain complex is much tinier, it has exactly the same homology as you would have got. So that's the amazing reason that we're talking about this at all. This is a very, very powerful engine for simplifying the sorts of chain complexes that we might have to deal with while giving us, without changing their homology at all. So in the next lecture, we're going to focus exclusively on these boundary operators of this reduced chain complex and see what on earth it takes to build them. And this is called the Morse chain complex, for reasons that have to do with smooth topology, and you can read about in the notes. This is the Morse chain complex of sigma, and in the next lecture, we will build this complex with our own hands. So see you there.